something like that. So it could be even larger than that, but that's sort of the order that we have been getting. So if we have an H in the reboiler, let's say of 1 kilowatt per meter square per Celsius degree, and we have a transfer area of 0.15 square meters, then this is more or less constant, right? And because you have, in one side, you have steam condensing, which means on that side the process is isothermal. In the other side, you have a liquid boiling, which means the process is isothermal. Then the LMTD is not L, it's just MTD. The mean temperature difference. There's no longer need to take any logarithm because the two sides of that heat exchanger in one side are at the same temperature, the other side at the same temperature. It's just delta T. So what's going to happen is that this is given by an old friend of ours, Monsieur Antoine, right? In its inverse form. Right? So we know the pressure, we know the temperature of the steam. And we know the temperature of the boiling thing depends on the composition, right? And for that, we can use not quite Antoine alone, but we can use the little loopy thing that you give it a composition and loopy thing and you get the temperature. Equilibrium is called. We are using Margulis for this equilibrium, but we could have used Wilson or Weber, no? Doesn't matter, some activity coefficient. So the point is that if you know XB, because we know the interaction coefficients, we know the two Antoine equations, we can get the temperature, no problem. So at any point, if we define the pressure of the steam, with the pressure of the steam, you get the temperature of the steam via Antoine. With XB, you get TB via, let's call that Antoine, Antoine's plus Margulis. And then, well, and then, of course, in that party, there's also Monsieur Raoult invited. Three guys, bunch of French people. And then Margulis was what? Margulis was Swiss, no? No, but he published his stuff in German.
Everybody did.
Austria.
It's Austria.
Austria, yeah, in Austria, yeah. Anyway, so we get this difference, right? Temperature of the steam minus TB. So in the end, if we multiply, I run out of space. Can I continue there? So the amount of heat that is going to be delivered is going to be equal to the heat transfer coefficient of the reboiler by the area of the reboiler by Ts minus Tb. And this is going to be equal to the mass, but it's going to be part, sorry, no, it's not going to be equal, it's going to be part of an enthalpy balance down here, right? And that enthalpy balance is going to determine LB. I'm going to show you the enthalpy balance in a moment. That's the enthalpy balance. So this is the amount of steam that we need, and that amount of steam then is going to be equal to, oh sorry, I want to just the amount of steam is going to be equal to oh, sorry, no. I wanted to write. Forgive me, please. The product of the steam multiplied by the enthalpy of condensation of the steam is equal to this amount of heat. This is the amount of heat that is released by the steam. Okay, so that is this little term here. And this, the derivation of this is in the notes. There's a detailed derivation of it. Okay? That is assuming that the temperature of B is equal to the temperature of VB, and there are no losses in that reboiler. If you want to be fancy and add losses in the reboiler, then the previous slide tells you how to do it and how to put them in the equation. So in this spreadsheet here is the calculation of each one of these guys following this, right? Refer to the corresponding places in the spreadsheet. So I haven't put the units yet, but I will. Okay, so these units, anyway, let's put the units there. Right, so these are, that is that, right? CVM multiplied by TV plus that enthalpy. And then the other ones you can see in the formula up there. But they are now, this K113 here is this X9 that can change a little bit depending on what you are doing with your, you know, you change your two lines, then that X9 changes a little bit, because X9 is this, right? You remember that when you are doing this to any stage operation, you call the things that come from the stage. So if it's a liquid coming from the stage down, the composition is X9, right? It's a vapor, it's X9. So it's this guy here, which happens to be the same composition of MP, no? So we calculate there, so, and then this one is the next one. So these four terms here are calculated here, and then the upper and lower term are calculated here for your viewing pleasure. So that's the upper term, and this is the lower term, and here's the ratio, which is now in moles per second. So the because B, that B there is in moles per second. So if you put this B here in front, this thing here is also in moles per second. So what you're going to end up getting is a non-dimensional ratio multiplied by B. So now the calculation of VB is down there too, so we can get VB and LB. And knowing this, we know that. This one we determine from the calculations of others. So we can then determine the slopes, and with the slopes we have the operating lines. So it becomes kind of a thing that loops on its own and gives us an approximation to how that column could be, right? So what you guys can do is have that there, and then see how it approximates your own experimental experience, right? More or less. The part, as I said, that's not quite included there is the cooling in the top, and we have that issue. I'm not so sure what the answer is to that one, and I'm not going to ask you to answer it in the exam, of course, because we haven't even figured out ourselves. But the rest, yes, you would like to be able to understand it. Okay, so this is sort of the overall general view of the thing. And so what do we have here is that these are the fluxes that we get, right, based on, I mean, obviously the fundamental thing you control is things like this, right? You control the flow rate, right, the field, and you control the reflux ratio, and you control the pressure of the steam, somewhere here, and that pressure of the steam gets converted to psi, kilopascals, and temperature, and then I have some funky quadratic thing to correlate the enthalpy of the steam as well within the range that we use to make the, because finding the enthalpy of the steam is the same. It's some basic enthalpy of evaporation and some correction for CP. So since the steam that we use it in a relatively narrow range, we can get a reasonable estimate of the enthalpy of vaporization with a quadratic equation. So what this little box is doing for you is it uses, you see the inversant one, right? So this is your PSIG, convert to PSIA, convert to kilopascal, and de-Antoinized to get the temperature. And then use some empirical correlations for the enthalpy of saturated steam, enthalpy of saturated water. The difference gives us an idea of the simplification.
Yes. Could you give us some examples of questions that would be good to practice using this spreadsheet so that we could be well prepared for the exam? Because I understand you're not going to give us the questions themselves, but I don't understand how we're going to use this to come up with answers that we're going to.
Yeah, so suppose I give you a data set, and I said, this is your data that you got from the lab, right? Can you explain why explain to me why your data are probably deviating from the behavior that you would get if it was sort of an ideal column by the different aspects that this model describes. And you could say, well, I find, for example, that systematically this model underestimates or overestimates because of this or because of that, which means that our column really has a very bad this or a very bad that, or something of that nature. Or you could, or we could ask you, if you were to use a model like this and you were to optimize something, for example, how would you go about creating a strategy in which you would play with those two parameters to optimize either yield or concentration based on the fact that you would have to adapt this model to the column to make it as realistic as possible? So you could say, well, I would take my data and I would look at what each tray did, right? Because I have 4 runs on my data, so I can more or less get a sense of what each tray is doing, and I would put a morphy efficiency for each tray, for example, right? And I would correct this H value that you have there is crappy, my H value is completely different, it's probably more like 1.2, and my cooling, I would change it to this, and this would give me something that resembles better my column, right? And then I would do this, right? So how would I use my experience with the column and this tool to actually predict something or be able to improve a process, right? Or between the experience in the lab and this little tool, we want to, for an industry that wants to do this process, they want to produce this, we want you to recommend a set of conditions. The question would be something of that nature. Does it make sense? Yep. So that you have this as a sort of, kind of a mini column there for you to adjust. But one thing is important is we want you to be able to explain why when you change something, how that creates like a like a cascade of effects, like I explained a moment ago. Right? If I increase the pressure of the steam, for example, then thermodynamically I necessarily increase the temperature, right? So I increase the temperature of the steam, then I increase the delta T that drives the force, and therefore I'm going to put more energy into the boiling. What happens when I put more energy into the boiling? I'm very likely I'm going to tend to drive this boiling more, so I'm going to tend to increase VB. And what is the slope here in my diagram? How is it defined, that slope? This slope is L over B, right? L over B. So if I increase V, I'm tending to lower my slope, right? Which in terms of this kind of stairs will tend to push it that way or move my XB down, right? On the other hand, by doing that, then I would probably kind of either push this way or the, and then explain that, the whole kind of thinking that you will have to do as an engineer, right? Engineers have to think that if I do something, it's going to have this consequence, right? So we want you to be able to explain that. And the little model, because it has the calculations kind of linked, should help you to follow that sort of, if I do this, it's going to do that. So not only did you do it in the lab, and you saw it happen, but we would like you to develop a little bit of a theoretical connection through the theoretical process through which it happened. And we think that a little thing like this might help you guys to do that. That's what we would hope. Yes?
I have a question in the Excel sheet. There's a value in C64 and it's not labeled. I'm not sure what it's called.
Yeah, this sheet is still a little bit unfinished. So, yes, C64. Sorry, C what?
C64.
We're in Canada.
What?
She said Z.
Oh, is that okay? It's right under the recursive. Yeah, 0.2914. Yeah, that value. What's
The value. Something multiplied by 1. That is when I was starting to get elite. Okay. I saw your
okay.
proof.
Okay.
I was in the middle of doing something and then I did it somewhere else. I forgot to do it. Thank you. Anyone else finds more of my remnants of my building process? There's probably going to be like a version 4 or something by tonight.
But even with the version that currently exists.
Yeah, this is already a good starting point because it works. It will
Can I
close the
finish a
loop and it
sentence?
will simulate your column.
Just have a question about the choice for asking us about this lab for the exam. Like, this was a lab where everyone struggled to understand the spreadsheet that was given.
Yeah.
And most people got the lowest marks in this lab.
Did
So,
they?
that's
Is
from
that a
what I've
fact?
heard, yes.
I'm just asking. I'm not challenging
Yeah.
that.
Yes,
That's
it
a-
was.
That's a fact.
You want to run away, Addison, or something? No?
So, just mainly
kidding.
because of, it took us a long time to understand what to do with the spreadsheet that was uploaded. So why choose this lab exactly to ask us when it's going to be 50% almost of the exam marks?
Did you see the text I wrote there, right? It had 3 components that were important: heat, mass, and momentum transfer, which are 3 essential components of chemical engineering, right? It has the level of complexity that is expected from a graduating class, from an excellent graduating class in chemical engineering, along with the other lab, which was the spray dryer. The evaporator lab had some degree of complexity, but a lot of its components were included in both of the other labs. And distillation is, I would say, kind of one of the traditional paramount sort of, I don't know how to say it, like it's the unit operation of the chemical engineers. It's almost what gave birth to chemical engineering. 2 things gave birth to chemical engineers: reactor design and distillation. So it seemed appropriate. Regardless of this type of complexities, which you guys are absolutely